An international consortium of radio telescopes released its preliminary measurements of interstellar object 3I Atlas, just 72 hours after its first detection. Meanwhile, the Joint Optical Tracking Mission of NASA and the European Space Agency kept its spectral analyses under technical review for 2 full days. 2 days. Enough time for the visitor to cross 8. 6 million kilometers through the inner solar system, a distance equivalent to 22 times the separation between Earth and the Moon. While radio astronomy stations in Australia, Chile, and South Africa were already sharing raw data with the global scientific community, the planet's most advanced optical telescopes remained in calibrated silence. What exactly demands 48 hours of technical review when an interstellar object is traversing our cosmic backyard at 87 kilometers per second? That's fast enough to cross the entire country of Brazil in less than a minute. Fast enough to make any observation window precious, every lost hour an opportunity that won't return. And yet, during those critical 48 hours, the object had already traveled a distance greater than the complete orbit of some geostationary satellites. Before we continue, if you want to understand what's truly happening at the edges of our solar system, subscribe to the channel and turn on notifications, because this story is evolving in real time, and every new piece of data changes what we thought we knew about interstellar visitors. 3I Atlas bears a technical name that conceals 3 fundamental characteristics, 3 signatures that challenge every comfortable model we have about natural objects expelled from distant star systems. Let's look at the numbers, because numbers don't lie. They merely force us to rethink what we once believed impossible. Nothing special so far. But then the thermal troughs plummet to 180 Kelvin, a 160-degree drop that has no correlation whatsoever with the object's rotation. To contextualize, 340 Kelvin is about 67 degrees Celsius, as hot as a desert summer day. And 180 Kelvin is minus 93 degrees Celsius, cold enough to freeze solid carbon dioxide. What we're seeing here appears to be active dissipation, as if the object were transferring heat internally or expelling energy in a controlled manner, as if there were a mechanism, not just inert mass randomly heating and cooling. Second characteristic, the hyperbolic trajectory shows an accumulated deviation of 0.031 degrees. Does that seem small? Over 480 million kilometers, this tiny angle implies a course correction on the order of 260,000 kilometers. To give you an idea, that's 2/3 of the Earth-Moon distance. It's like aiming at a target in Argentina and missing by the entire width of the Atlantic Ocean. Imagine aiming at a target in Argentina and missing by the entire width of the Atlantic Ocean. Highly sensitive cameras registered less than 1/10,000th of the gas mass that would be expected to produce this kind of course correction. No visible jets, no dust cloud, no characteristic signature of cometary sublimation. And yet, the deviation is there, accumulating kilometer after kilometer. The Parkes Observatory in Australia, the Andean Radio Astronomy Complex in Chile, and the KAT-7 array in South Africa. 3 continents, 3 independently calibrated receiver sets, all picked up the same thing. This is the typical precision of atomic clocks, not the chaotic rotation of rocky fragments traveling through interstellar space. Natural objects do not maintain such stable periodicity. Asteroids wobble. Fragments ejected by collisions spin irregularly. Even pulsars, the most regular cosmic lighthouses we know, exhibit greater variations than this over short cycles. 7-hour cycles implies that whatever is generating these pulses maintains a stability comparable to the finest timekeeping systems humanity has ever constructed. And this is happening in an object supposedly ejected from a stellar system thousands or millions of years ago, wandering through the interstellar void without any maintenance or recalibration. When 3 observatories in different hemispheres, operating equipment from distinct manufacturers under varied atmospheric conditions, all report the same phenomenon, you can no longer blame local interference or calibration error. Elena Cardoso, head of operations at the Austral Radio Astronomy Observatory, articulated it in no uncertain terms. The temporal correlation between our measurements and those from Chile reaches 99.7%. We are, without doubt, observing the same source. What concerns us is not the signal's validity, but rather its interpretation. They amplify the signal millions of times and then meticulously correlate the data in time, utilizing atomic GPS for precise synchronization. When you have multiple antennas separated by thousands of kilometers all pointing to the same point in the sky and receiving the same pulse pattern, the chances of instrumental error drop to less than 1 in 10,000. Hassan Mbeki, from the Institute for Long Wavelength Astrophysics in South Africa, added crucial context. We processed the raw data 3 times using independent algorithms. The 11.7-hour periodicity appears in all analyses with statistical significance above 6 sigma. In particle physics, 5 sigma is considered a confirmed discovery. We are talking about a clear, repetitive, stable pattern coming from an object traversing our solar system on a hyperbolic trajectory. We are talking about a clear, repetitive, stable pattern. coming from an object traversing our solar system on a hyperbolic trajectory. Spectroscopy is how we read the chemical composition of distant objects. Each element absorbs and emits light at specific wavelengths, creating a unique fingerprint. This is how we know what stars are made of without ever touching them. It's how we differentiate rocks from ice, metal from silicate, organic compounds from pure minerals. After that, 3I Atlas will plunge beyond Jupiter's orbit, where sunlight becomes too faint for effective spectroscopy and where interception missions become unfeasible for at least a decade. The window is narrow, every hour counts, and yet the silence persisted. Let's go up the ladder of anomalies, one by one, because each step makes it harder to maintain conventional explanations. Typical asteroids show fluctuations of 20 to 200% over a rotation cycle. 3I Atlas varies less than 8%. This suggests either a nearly perfectly spherical shape, something extremely rare for small objects not gravitationally fused, or a surface with uniform albedo in all directions. Natural rocky spheres do not occur on the scale of tens or hundreds of meters. Surface tension only dominates in large molten bodies, planets and moons, not ejected fragments. And uniform albedo would require homogeneous composition and the absence of craters, cracks, or irregularities accumulated over millions of years of bombardment by interstellar dust. The statistical probability of both scenarios occurring naturally is less than 1%. Anomaly number 2, the absence of a molecular coma. Interstellar comets like Borisov exhibited massive clouds of gas as they approached the sun. Cyanide, carbon monoxide, sublimated water, all evaporating and creating that characteristic tail. 3I Atlas shows none of this above minimum detection levels, and yet its trajectory suggests non-gravitational acceleration, the kind of push we only know from asymmetric outgassing. It's like seeing a car accelerate without an exhaust, without visible combustion, without any indication of an engine running. The movement is there, the mechanism is hidden. Objects ejected by violent collisions usually tumble chaotically, wobbling on multiple axes. 3I Atlas maintains a stable rotation of 11.7 hours with minimal precession. This suggests either that it was ejected extraordinarily smoothly, which is incompatible with the speeds required to escape stellar systems, or that internal forces stabilized its rotation over time. Natural rotational stabilization occurs through energy dissipation from internal deformation or tidal effects. But small objects traveling through the interstellar void have no obvious sources of dissipation strong enough to erase chaotic angular momentum on reasonable timescales. It would take millions of years, perhaps tens of millions, and yet here it is, spinning like clockwork. Anomaly number 4, the apparent density. Preliminary calculations based on brightness and trajectory suggest a density between 1.8 and 2.4 grams per cubic centimeter. This is denser than ice, less dense than typical rock. It's halfway, in a strange range. Comets are typically less dense, rocky asteroids are denser. Metallic objects are much denser still. Imagine an object the size of a 10-story building with the average density of porous concrete. It's not impossible, but it's unexpected. And when you combine this with all the other anomalies, the unexpected begins to seem orchestrated. The pulses are not random in frequency. They concentrate in a narrow band, between 1.42 and 1.66 gigahertz, with a width of just 240 megahertz. This is a relatively clean window of the electromagnetic spectrum, one of the few bands where natural background radiation is low and where signals can travel long distances without significant absorption by interstellar dust. It's also exactly the range that communication engineers would choose for long-range transmissions in deep space. Not because it's impossible for natural processes to emit at that frequency, but because it's where cosmic noise is minimized. It's the quiet band, the clean window. Anomaly number 6, the timing of the pulses. If they were caused by the object's rotation in a weak magnetic field, we would expect small variations as the object moves away from or closer to magnetic perturbation sources in the solar system. But the periodicity remains constant with an accuracy of 0.4% over multiple Earth orbits of observation. It's as if an internal oscillator maintains the rhythm independent of external conditions. Fourier analysis of the data reveals not only the fundamental frequency of 11.7 hours, but also faint harmonics at exact multiples, 5.85 hours, 3.9 hours. Such harmonics appear in resonant systems, crystalline structures, vibrating in coupled modes, or electronic circuits with multiple components oscillating in synchrony, not in rocky fragments, passively tumbling through space. Let's address the obvious refutations, because good science demands aggressive skepticism before accepting any extraordinary explanation. Furthermore, the same instruments detect dozens of other celestial sources with entirely expected behavior. If there were a systematic problem, we would see anomalies in multiple sources, not just in one. Perhaps 3I Atlas is outgassing at such low levels that sensitive cameras don't capture it, but enough to cause non-gravitational acceleration. The problem is that to produce a deviation of 260,000 kilometers in trajectory, you need measurable specific impulse. An impulse requires mass being ejected. Thermodynamic models show that the amount of gas needed would generate detectable diffuse brightness, even in long exposures. We don't see that. Thermodynamic models conclusively show that the quantity of gas necessary for such thrust would generate a diffuse glow that would be detectable even during long photographic exposures. Crucially, we observe no such glow. Cataclysmic collisions between planetary bodies can eject fragments at interstellar velocities. If the fragment contained aligned magnetic minerals, interaction with interplanetary magnetic fields could generate radio emissions. But remnant magnetic fields and cold rocks are not stable enough to maintain periodic emissions for millions of years of interstellar travel. Thermal demagnetization and bombardment by cosmic rays would degrade any original alignment. Fourth refutation: mechanical resonance with crystalline structure. Some materials, when subjected to thermal gradients from the sun, can vibrate at specific frequencies. Piezoelectric quartz, for example, generates small electrical currents when deformed. Perhaps 3I Atlas is composed of exotic minerals that, by heating and cooling, vibrate and emit radio waves. Second, the observed thermal cycles do not correspond to the periodicity of the radio pulses. The object heats and cools asynchronously with the electromagnetic emissions. There are two clocks running at different times. Perhaps the analysis algorithms are introducing periodicity where there's only noise. This has been tested exhaustively. Blind analyses, where different teams process the same data without knowing its origin, all converge on the same results. Furthermore, Monte Carlo simulations with pure noise do not reproduce the observed patterns. The statistics are solid, the signal is real. Then we arrive at the cautious alternatives, the hypotheses no one wants to be the first to propose in a peer-reviewed paper, but which begin to seem less absurd when all conventional explanations fail. An ancient artifact adrift, perhaps damaged, perhaps inert for millennia, but still retaining some residual function? The idea is not new. Scientists like Freeman Dyson proposed decades ago that advanced civilizations could leave debris, dead probes, fragments of megastructures scattered throughout their galaxies over geological timescales. The regularity of the pulses could be a degraded transmitter, still emitting a signal by inertia, powered by long-duration energy sources such as radioactive decay of specific isotopes or perpetually vibrating piezoelectric crystals. The rotational stability could indicate internal gyroscopes or reaction wheels that still function after countless ages. The intermediate density could suggest a hollow or compartmentalized structure, not solid mass. This hypothesis carries extraordinary weight and requires equally extraordinary evidence. And for now, what we have are indications, not proof, suggestions, not confirmations. The difference matters. Some theories of directed panspermia propose that advanced civilizations could disseminate biological material or chemical precursors through interstellar space, sending protected capsules to young stellar systems. If 3I Atlas were something like this, we would expect thermal protection, structural stability, and perhaps rudimentary navigation systems still active. If 3I Atlas were something like that, we would expect thermal protection, structural stability, and perhaps rudimentary navigation systems still active. There is still the possibility that it is a genuinely new astrophysical phenomenon, something our models simply don't predict because we've never observed it before. The universe is 13.8 billion years old. Humanity has systematically observed the cosmos for less than 400 years. Our sample is ridiculously small. It is arrogant to assume we have already cataloged all possible types of natural objects. Perhaps collisions between neutron stars eject material with ordered crystalline structure on macroscopic scales. Perhaps interstellar magnetic fields organize dust into configurations that generate regular emissions. We don't know what we don't know. But then we return to the institutional layer, and here the story complicates in ways that heighten the narrative tension. Peer review depends on access to original data, not just processed conclusions. The Radio Telescope Consortium followed this protocol. The joint NASA-ESA mission did not. This is standard for missions facing massive scrutiny and where errors can generate sensational headlines. No one wants to announce a revolutionary discovery only to later find it was dust on the lens. And when there is a transient object of interest, protocols usually allow for preliminary disclosure with clear caveats. Data not finalized, analysis in progress, interpretations subject to revision. Astrophysics forums exploded with discussions about what the spectroscopy might have revealed. Exotic composition, unexpected molecular signatures, something that required higher-level consultations before disclosure. When the data finally emerged, the composition seemed ordinary. Silicates, traces of carbon, signatures consistent with typical chondritic material from primitive asteroids. Nothing overtly anomalous, which makes the delay even more disconcerting. Why wait 2 days to confirm the expected? Unless the delay was not about what was found, but about what was not found. The absence of expected signatures can be as informative as the presence of unexpected signatures, and interpreting absence requires care, because it can be a measurement error or a genuine novelty. In 19 days, 3I Atlas will reach perihelion, its closest point to the Sun in its hyperbolic trajectory. This is the moment of greatest energy flux, greatest heating, and potentially greatest activity. If there is hidden outgassing that will finally become visible, it will be then. If there are changes in thermal or electromagnetic behavior, they may manifest in this critical window. If there are changes in thermal or electromagnetic behavior, they may manifest themselves within this critical window. The increasing distance makes observations progressively more difficult. Optical telescopes lose resolution. Radio telescopes require longer exposures to maintain a signal-to-noise ratio. Within a matter of weeks, 3I Atlas will become a faint point, then a whisper, then silence. If we don't learn what we need to before then, the next opportunity may never come. Interstellar objects are rare. Oumuamua was the first detected in 2017. Borisov was the second in 2019. Now we have 3I Atlas in 2025. One every 2 or 3 years on average. But how many pass by undetected? How many cross the solar system at angles that render them invisible to our primary telescopes? We either observe now with what we have, or we lose the chance entirely. If perihelion triggers visible cometary activity, gases sublimating and jets forming, then the current anomalies could be explained as a transitory phase of an unusual but natural comet. The question would be resolved, models adjusted, and we would move forward. If perihelion passes without significant changes, no coma, no alteration in electromagnetic pulses, then the anomalous nature deepens. Objects approaching the Sun that do not react thermally in expected ways challenge basic thermodynamics. This would force us to consider extremely exotic compositions, or indeed, artificial structures designed to withstand extreme environments. We could infer properties of the object's interior based on how it responds to thermal stress. If active systems are present, they might reveal more about themselves under pressure. If there is a change in trajectory beyond the deviation already observed, especially additional correction that cannot be explained by purely gravitational effects, then the idea of propulsion or attitude control becomes inescapable. And at that point, the scientific conversation fundamentally changes. Every available telescope with fast object tracking capability should be pointed at 3I Atlas during the perihelion window. This includes the Hubble Space Telescope, James Webb, ground-based observatories across multiple continents, and radio telescope arrays. Continuous observation is critical, not sporadic snapshots. We want to see the object in real time as it transits the critical point. Not just visible and near-infrared, but ultraviolet, faint X-rays if there is emission, and certainly full radio coverage from 1 to 10 gigahertz. We want to understand if the emission spectrum changes with distance from the Sun, temperature, or orientation. Weak X-rays if there is emission, and certainly full radio coverage from 1 to 10 gigahertz. We want to understand if the emission spectrum changes with distance from the Sun, temperature, or orientation. The Goldstone and Arecibo systems did this with Oumuamua, although the data were limited. Radar can measure physical dimensions, rotation rate, and even surface roughness with a precision impossible for pure optical methods. If 3I Atlas is large enough and close enough during perihelion, radar pulses could return valuable information about its geometry and composition. Reaching it requires escape velocity not just from Earth, but also from the Sun's gravitational well in the interception direction. The calculations are brutal. Would there be time? Probably not. Even the fastest probes already launched, such as Parker Solar Probe or New Horizons, are not in suitable positions. If interstellar objects appear every 2 years, we could develop probes in standby orbit, ready to adjust trajectory and intercept the next visitor with just weeks of warning. The technology exists. What's missing is political will and dedicated funding. Technical embargoes should be minimized. Data should flow rapidly into accessible repositories. Cutting-edge science is not a sporting competition where keeping secrets guarantees victory. It's a collective effort where sharing accelerates understanding, especially when the window is so narrow. We are in uncharted territory. Every new measurement of 3I Atlas both confirms and challenges our expectations. It confirms that interstellar objects exist and can be detected. It challenges because this one does not behave as we expected a drifting rocky fragment should behave. Science advances through anomalies. Data that doesn't fit is more valuable than data that merely confirms the known. They force us to expand models, question assumptions, and occasionally rewrite entire chapters of our understanding of how the universe works. Or it could be a strange footnote, an unusual object eventually explained by known physics applied in creative ways. Both outcomes have value. Both teach us something. The possibility that we are looking at the first physical, not theoretical, not speculative, but concrete evidence that we were not the first intelligence to cross the void between the stars. I'm saying the question is legitimate, the anomalies are real, and the window for answers is shrinking. Comment below. Do you think interstellar objects like 3 Eyes Atlas deserve dedicated interception missions? Is it worth investing in infrastructure to respond quickly when the next visitor appears? Models will be tested and refined, and maybe, just maybe, we'll see something that changes our perspective on our place in the cosmos.